So let's take a look at Unit 6, how computers work. Now, we had how the internet works, then we did algorithms, and now we're back to how something works. What we're really doing here is another one that's not about programming. This is about learning some things that you should have as part of your background knowledge if you work with computers. Okay? So one thing that I will mention is that there's a lot of abstractions. I mean, ultimately, how do computers work? Because that's the way electricity moves, right? But what we're doing is we have abstractions on top of things like moving electrons that help us understand computing. And so this is just one abstraction inside another abstraction. I tend to think in terms of like Russian dolls is what this brings to mind. So here's the abstraction hierarchy. At the very bottom, we have the analog domain. What's the analog domain? Electricity and magnetism, right? That's how electrons move, electric fields, magnetic fields, conductors, properties of, that's physics, okay? On top of that, we have the digital domain. What's the digital domain? We're thinking in terms of ones and zeros, right? I don't care what your voltage is. It's either a 1 or a 0. That's the way I'm going to think about it. Voltage for this line is either 1 or 0. So if I send you 0.1 volts, 0. If I send you 0.6 volts, 1, right? And the answer is always going to be either close to 0.0 or close to 0.5. That means that I can say whether it's 0 or 1, okay? And then we have the software domain. And what's the software domain? Well, those are all the programs we use, right? So when I'm using a computer, what I'm actually doing is I'm using, say, my web browser. That's the software, right? It's running on a monitor. Okay, that's kind of the digital world. So, I'm saying this pixel should be this color, right? That's digital. And then ultimately I'm saying that why? Because electrons are flowing this way instead of that way. That's physics, right? So that's kind of the hierarchy that they should appreciate. Okay. Now, in the software world, just talking the software world, I'm going to program in some computing language. Our students are seeing Snap. Okay, our students have heard of other languages. They've heard of Python. They've heard of JavaScript. They've heard of Java. They've heard of C++, and so on. They've heard of other languages that aren't actually languages. They've heard of HTML, right? That's not a computer language. That's a desktop format. They've heard of Excel. It's not a computer language. That is a spreadsheet, right? But they've heard of a lot of other computer languages, and they should know, they need to know that the languages are going to spread apart by high level, okay? So high level languages are very abstract, Snap, Scheme, okay? Some other languages are kind of intermediate, like Python and Java, and then there's languages that you're programming closer to the architecture, closer to that digital abstraction, like C and C++. So there's a spectrum, and why should you choose a high level language? Because it's closer to the human end, right? So I can actually describe my algorithm to you in a way that is easier for me to describe, easier for somebody else to read when they read my program. High-level languages are good for that reason. So why do we still keep around low-level languages? Because sometimes I have to write code that actually needs to be close to the machine. I can't do it in Snap. Okay, I'm going to have to do it in a low-level language like C or C++. And because of speed. The reason that I need to be close to the machine is because I need to go fast, and so I need to exploit some machine properties. You're not going to do that in Snap. You're going to have to do that in C, C++. So that's what they need to understand. The other thing that you learn from this little discussion is that the languages are not the important thing. So let's say that I want to write a program that talks on the internet. It's a chatbot, okay? I want to write a chatbot. I can actually write that in C. I can actually write that in Snap. So which one should I pick? Low level, high level. Of course, the highest the better, right, for the human. But the reason I may have to go down is not so much for the abstraction. It may be because, let's say that Snap does not have the ability to talk on the internet, but JavaScript does. Okay? Now, why does it? Because somebody wrote a library that makes it easy to talk on the internet. Okay? They wrote a library. That means the JavaScript could the whole time. Snap actually can the whole time. But it might be difficult to do because somebody hasn't written some body of code that makes it easy to do, right? That's what a library is. So for example, can you do trigonometric substitutions in Snap? Hey, you actually need to have sines and cosines and tangents and stuff like that to use trigonometric functions. Hint, Snap does. But let's assume we didn't, right? You could still do it because I can actually use mathematics to define my own sine and cosine function. Hardcore, I define my own sine and cosine function. That's just a lot of work. In other languages, they already exist because somebody already put in that work. That's what a library is. We like libraries. They make life easier, okay? So the students should learn about that, okay? Again, we're just walking down this hierarchy. Beyond the software, then the software talks to the hardware. That layer between the software and the hardware essentially provides a way of thinking about itself, right? This is what I am. I have a memory. I have a processing unit. I have a disk drive, and so on. These are abstractions, actually, okay? And they provide a high-level view of the hardware so that the software can communicate. We actually call that the architecture of the hardware, okay? Things that it might show me are components like memory. If I actually start looking at memory carefully, I see that it contains some very complex circuits that try to remember I'm a 1, I'm a 0, right? We call those integrated circuits, okay? That's just a way of building them. It's actually a manufacturing way of building circuits, integrated circuits. If I look inside integrated circuits, I start seeing little things, motifs that reappear again and again, and I might recognize those and call those gates, right? So I have this wire, I have this wire. If both of the wires are on or ones, when they combine, they produce a 1. If either one is off, when they combine, they produce an off. They combined in this little thing here, right? What's this thing? It's acting like an AND. If they're both on, then it's on, otherwise it's off. That's AND. We call that circuitry an AND gate, okay? And so those are logic gates, right? Of course, if I peer inside a logic gate, what do I find? I find resistors. I find transistors, okay? And so what did I just discover? Oh, electronics components are in here, right? And how do electronics components behave? That's a circuits class, right? And they'll teach you about resistors, Ohm's law, stuff like that. They'll also teach you about transistors, a lot fancier. Checking to see if there's any physicists around. There aren't, so I can tell you that this is where you stop, okay? Although, if you actually want to peer inside a resistor, then you take physics, right? And they'll actually explain to you what's happening as the electrons are flowing through the thing, and they call up. Anyway, that's physics underneath all of this stuff, right? So that's your abstraction hierarchy. Just a little side thing. If I do go all the way down, I'm going to actually find things like metals, right? You know, actual raw materials that are connected in different ways. Like I said, this goes all the way down to semiconductors. And semiconductors, the only way to explain them is to talk about quantum physics. So it's pretty advanced. That's why we don't go there, right? We stop at like AND gates. But anyway, that's if you actually go all the way down. And some of your students are going to want to go all the way down. Keep going down, and you find those very exotic metals. Some of those are called rare earth metals for a reason. They're not very common, okay? They're pretty rare. And that means that we're going to run out at some point, and then we won't have enough materials to make computers, right? That's something that's happening, that's something people talk about, right? Where do a lot of the rare earth minerals come from? China. Okay, that's something that people are talking about right now. Some other minerals that you find in there, by the way, like gold even, they're called conflict metals. And it's not that they're hard to find, it's just that the places that we're finding them are places of the world that are, well, you know, they're like the Old West, okay? So they might be run by essentially little militant chieftains, right? And who will say, yes, go in and dig for that metal. I'm not going to pay you anything, but I'll let you live if you dig all day for that metal, and then they sell it to us to put in computers. And so, you know, you might have heard, for example, of like blood diamonds. The same thing is happening with computers. And so we're becoming more aware of that and trying to address it. Okay, second lab. Now we talked about the hierarchy of computers. The second thing is to talk about data representation. So how to actually represent data on a computer, right? So computers are digital devices. We should know that, okay? What does it mean to be a digital device? Digital actually means that it has distinct levels. So where does it come from? Digital, digits, right? They're distinct, they're separate, right? So it's either this one or that one or this one or that one or that one. It's not in between. That's not a digit, right? It's here or here. That's actually great. Because let's say that I send you a signal across a wire, it's a voltage, okay, to represent either 0 or 1. And I know that the lowest possible voltage is 0, the highest possible voltage is, I'm going to be gross, I'm going to say it's 5 volts, okay? Well, if I actually measure 0.7 volts, I know that you meant 0. You did not mean 5, okay? So I can correct the distortion in the signal, right? I can correct it, you know, because I know that there's no way it was 0.7. I know it's not that. It's either 0 or 5. So it must be 0. If I get 4.3, same thing. That's actually a 5. That's not 0, right? So I correct little errors as they happen, right? That's why digital is better than analog, okay? Because in analog, if I tell you that it's 0.7, you just have to take my word for it. It must be 0.7, okay? You can't say, oh, you meant 0. No, you could have meant 0.7. That's why digital is good, okay? So the easiest digital abstraction, we don't have 5 digits. We got 2 digits. It's either 0 or 1, right? That's the easiest one. And we call those bits. They're binary digits. I don't know who came up with that. Those bits, 0 or 1, we collect into something called bytes, okay? And a byte in modern computers is an 8 bits, right? And then we collect those into words. In modern computers, you're talking either 4 or 8 bytes per word, which means either 32 or 64 bits per word. A word is kind of the natural chunk that the machine uses to deal with memory. So it loads memory a word at a time, okay? Okay, I got zeros or ones. What can I do? Well, I can represent text, okay? And I can represent text in a couple of different ways. Kind of the naive way, which was what the first computers did, okay? I mentioned Turing. Turing was actually British, but after World War II, a lot of the kind of pioneering working computers moved to the US, and so it was Americans who figured this out. And they went, I want to represent words in a computer. That means I need to represent letters in a computer. Hey, there's only 26 of those. Oh, upper and lowercase. There's only 52 of those. I need digits, 0 through 9. There's 10 of those. 62. Punctuation, comma, period, exclamation mark, question mark, space. You know what? 10 of those maybe? So 80 characters is plenty. All I need is 80 characters. And so 8-bit bytes can represent 256 different things. 80 characters easily fits into 8-bit bytes. That's how we're going to do it. This number is that letter. This number is that letter, and so on. Okay, that is a simple code. It's called the Ascii Code. Okay, and only problem was that it was done by Americans, and so they forgot about little things like, you know, in Spanish you can have an E with a tilde on top. Darn, that's another letter. I meant 81, uppercase, 82. In French, you can have letters with commas underneath them. Okay, so now I don't need 80. I might need 100 and something. Yeah, it's okay. Don't panic yet. And then the Germans. What is that? 2 S's, really? Okay. All right, so I need a few more letters. Thank God. Okay, don't panic. We still got it. And then we started selling computers to the Asian countries, and we went, oh, we are so doomed. So at that point, we invented a whole new way of storing letters in computers. We call that UTF. U is universal. And so now 8-bit bytes are not enough, but it's still something that's solvable. And this is a problem that has been solved. Your students should know at least about ASCII, okay? And I mean that. I'm not saying they need to remember ASCII. They need to understand the concept, because some of the questions will say, here is an ASCII table. Which letter has more ones in its code, A or B? Gotta hate that problem. But they'll have stuff like that that force them to think about changing letters to numbers. Bits can represent numbers, right? I mean, you know, so that's something else we can do. I have a whole bunch of zeros and ones. So you know the obvious way to represent numbers is to do something that we learned about probably in 2nd or 3rd grade and then forgot because it wasn't useful, and that was binary representation. Oh, it's coming back. So binary representation, change of base. Do you remember that from elementary school? We do that in computers all the time. So for example, the number 12 is 1100. This is actually gone over in lab 2, so I'm not going to go through it here. But why is it 1100? Because that leading 1 is not thousands, it is eights. And then it's not hundreds, it is fours. 8 plus 4 is 12. Okay, 25, 11001. That leading 1 is 16, plus 8, 24, 00, plus 1, 25. Okay, so that's how we represent numbers. Now, computers don't use 5 or 4 or 6 bits. They're going to use 32 bits for integers, even 64 bits for integers. Why? That's how big our words are. And like I said, words are kind of the natural unit for computers. So 32 zeros and ones, 64 zeros and ones. None of us is going to read through that. So what we do is we do it in hex. Okay? Hex basically takes every 4 bits, every byte, and turns it into a single letter. Okay, so 12, which is 1100 in binary, is actually 0000000. I mean, it's 64 bits, and then 1 capital C. The C actually is 1100. 25, lots of zeros, leading zeros, and then 1, 9. The 1 is that 001 at the front. The 9 is the 1001 that follows it. Every 4 bits becomes a hex digit. Okay, your students need to know how to go from decimal to binary, from binary to hex, from hex to binary, from binary to decimal. And I find that it's useful to go directly from decimal to hex and from hex to decimal, simply because sometimes the binary gets to be too big. So it's kind of nice to kind of have those 3 bases, just be able to go from one to the other. Okay, one minor problem that your students need to know about, because I'm using, say, 32-bit integers, I already have a largest integer that I can store. Just like if I tell you you have 4 digits, right? Then that means you can go up to 9,999, but you cannot store 10,000. That takes 5 digits, right? So I already have a largest number that I could possibly store. So is that a problem? Yeah. And the reason that I have a problem is that I can write some programs, okay? Like, for example, you give me the number n, I give you 2 to the n. Okay? So if you give me 1, I give you 2. Give me 2, I give you 2 times 2, 4. Give me 3, I gave you 2 times 2 times 2, 8. Give me 4, I gave you 2 times 2 times 2 times 2, 4 times, 16, and so on, right? If you give me 100, I give you 2 times 2 times 2 times 2 times 2, all the way up to times 2. How many digits does that take to store? In base 2, it takes 101 digits. I've only got 32 bits. I can't store a 101-bit number in there. So what do? I can actually store big numbers if I want to, right? Because, for example, I want to store something that has 100 zeros and a 1 in front of it. Why don't I just store that? A 1, a 0, a 0, a 0, like in a list that has 101 characters. Why not, right? So I could do that. That's called a, quote, big int. Really creative name, huh? Big int. So if you have big ints, you can actually do anything you want. Again, this is a trade of time. If you use big ints, you can store numbers that are as big as you want. But plus, minus, times are slow operations. If you use regular 32-bit integers, those operations are fast. They're done by the hardware. Bad news? I can only get up to this large number. So that's, again, that's a trade-off your students should understand. How about real numbers? Real numbers, yeah, that's kind of a pain. Actually, the traditional solution is to use something called a floating point number, okay? And floating point number, the way I want you and your students to think about it is that it's numbers in scientific notation. So I can have 1.2 times 10 to the 5, okay? So that's like what, 120,000 or something like that? That's the way we store them, 1,200,000. The really important part here is that all I need to remember is the 12, the 1 and the 2, right? Because it is simply implicit that there's a decimal point between the leading digit and the rest. They go between 1 and 10, okay? The other thing I need to store is the exponent. 10 to the what? 5, okay? So all I need to store is 12 and 5. Those are just 2 integers. We already know how to store integers. So if you store 2 integers, that is a number in exponential notation, or in scientific notation, that is floating point, okay? Essentially, a couple of minor details. It's not 10 to the, it's actually powers of 2, okay? Because computers work in powers of 2. Doesn't make that big a difference. Something else, I only have so many bits for the 12 part, and I only have so many bits for the 5 part, okay? The exponent and the mantissa is what they're called. I only have so many bits, which means they can only get so big, right? So how does that actually affect it? Because my exponents are only so big, I can actually only store numbers up to here. That's you know, it's a really big number, but still, there's a limit, okay? That's the exponent. In the mantissa part, because I can only store so many digits, what it means I only have so much precision, right? So let's say I can only store 7 digits. Then I can store the number 1, 2, 3, 4, 5, 6. No problems, right? But I cannot store the number 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? By the way, I can't store the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, right? It'll store it. You might say something like 1.23456 times 10 to the 9th, right? Okay, but I lost precision, right? It's not exactly what I had in mind. I lost precision. So with real numbers in computers, I have a limit in size, and I also have a limit in precision, right? That may or may not affect you. Okay, compression. What's the whole point of, I'm sorry, before I get there. I'm working on representation. I told you how to represent characters. I told you how to represent numbers. Of course, we can do more than that. One of the things that they'll want you to know how it's represented is colors, right? So what do I do with color? There's different ways of representing colors. They're known as color spaces. So two very common ones are the RGB red, green, blue space, and I'll talk about that in a second. Or for example, I might have the HSV space, okay, which is hue, saturation, and brightness. Those are different kind of spaces. Artists will actually happily use different types of color spaces for different reasons. But let's just talk about kind of the traditional way to represent colors in computers, and that is red, green, blue. So what you'll do is you'll say this particular color has this much intensity in red, this much intensity in the green frequency, this much intensity in the blue frequency. The reason that's justified is because the way our eyes work is we have rods and cones, and we detect colors specifically in reddish frequencies, greenish, bluish frequencies. So that's why it's kind of justified by that physiology. But anyway, how many different shades of green, how many intensities of green can you identify? Coincidentally, is 256. Coincidence? I think not. I think they just said that's plenty and run with it. So it takes 8 bits to represent a red intensity. That's a number between 0 and 255. Same goes for green, same goes for yellow. For blue. If you list them all, then you get white. That's red, green, blue, full intensity. If you list them all 0, you get black. Absolutely no color shows, right? And you can create lots of subtle shades of color by varying those numbers. Okay, so your students should know about the way we represent color. And that actually leads to the way that we represent, say, a picture. What is a picture? It is a two-dimensional grid of colors, right? You might say a matrix of colors if you want, right? If you want to push your students in that direction. If not, just say a square grid or a rectangular grid, color, 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 color. That's how we represent pictures. Just kind of order of magnitude. Let's say that you have a 1 megapixel camera. How do I get that? I get 10,000 columns, 10,000 rows. 1,000 each. That is 1 million total little color elements. We call those pixels, picture elements. Okay, that's 1 million of those. Each one of those is red, green, blue. So you're talking one picture, 3 million bytes. That's big, right? You take your camera, picture, 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 picture. Why is it full? That's why. Okay. So by the way, that's only a 1 megapixel camera. You remember the last time you had a 1 megapixel camera? You're probably walking around with 6 megapixels or something, right? So we need even more space. So that's a problem. So what we want is to be able to shrink that file, make it smaller so that I can take even more pictures, right? That's called compression, right? I want to make the file smaller. Whenever I talk about compression, I need to talk about decompression. I mean, it's very easy to make a file small. The hard part is making it small, but then be able to extract the large file from it, okay? By the way, the pictures you see here, okay, one of these is compressed, the other one is not, okay? See if you can tell the difference. That's an unfair challenge because I'm putting those in a tiny area of a computer screen. Good luck finding a difference, okay? So it's a biased experiment. But anyway, it turns out that we have kind of a choice that we can make. Because you, for example, might be a photographer, okay? And you might say, I need to be able to recover the original file exactly as it was when I compressed it, okay? Because that's part of my art, okay? No, it is not good enough to say that this is really, really dark. I need to know the exact darkness, okay? So if you feel that way, then you need what is known as lossless compression, which means that you lose absolutely nothing by compressing and then expanding back out, decompressing, okay? If you don't care about that, if you're like, yeah, I just want it to kind of look the same, right? Then you can live with something called lossy compression. That means that it will make it small. When you make it back, what you get is an approximation. It's almost the original file, but maybe not exactly. Maybe this is 25 in red instead of 24 in red, okay? Here's why we have that trade-off. I mean, obviously, if it didn't make a difference, then we just always go for lossless, right? I lose nothing. But the reason that you might want to go for lossy is that when you compress with lossy compression, it's kind of an easier problem you don't have to come up with the exact same image, only an approximation. So you might actually be more aggressive in your compression, make the files even smaller. Okay? I'm sure you've heard about JPEG files. JPEG files are compressed using lossy compression schemes. Okay? The lossless compression, that's for the pros. Okay? And the files are actually a little bit bigger because you can't be as aggressive in making it small. So that's a trade-off in compression your students should know about. Okay, lab 3, which is actually the last lab in this unit, is a brief history of computers. So there's a timeline. By the way, be very careful with the x-axis. That is not in a linear scale. That's logarithmic, okay? So we go back to the very first things that look like computers. That's like 20, 30,000 years ago. I mean, we're really stretching what we mean by computers. We see the abacus from the Chinese, and then all the way to the right edge, where you're going to find things like, Windows, okay, or Siri, right? So that starts appearing towards the right. Last thing they want you to kind of appreciate as part of that historical thing is Moore's law. Moore was one of the founders of Intel, and he observed that every year his chips that he was creating at Intel actually essentially doubled in size, right? And what he meant was this. This year I can put in 1,000 transistors on a chip. Next year it's going to be 2,000. The year after that, double, 4,000. After that, 8,000, 16,000, 32,000, and so on, right? So it just explodes. If you're not familiar with exponentials, this is the picture you want to think. Nothing, nothing, nothing. Oh, look, it's starting to grow. That's what exponential functions look like, right? You don't see anything happen, and then you start noticing, right? So for example, if you have like an epidemic that's growing exponentially, somebody got sick, don't care. 2 people are sick, my God, 4 people are sick, nothing, right? Next day, 16,000 people are sick. Oh, I need to start worrying. 2 days later, 64,000 people are sick, and now I can deal with it. Okay, that's exponential growth. So Moore actually said, my God, the number of transistors on a chip is growing exponentially. Okay, that law then became, instead of number of transistors, how fast the computer ran. So my computer runs 4 megahertz. That's 4 million cycles per second. Oh my God, this is so fast. The next year, they now have computers running at 8 megahertz. Damn, that's cool. I wish I waited a year. Next year, 16 megahertz. Before you know it, why are we using gigahertz to talk about how fast the computer is running? When did that happen, right? That's just 10 years difference, and I'm already at 1,000 megahertz level. That has stopped. Moore's law has essentially stopped. The reason for that is that we've gotten to the point that we can no longer make computers go faster, because we're running into actual physics limitations, quantum limitations. So now, I have a computer that has 1 CPU on it. That's so old school. Now computers have 2 CPUs. Oh, why? My computer has 4 CPUs. I have a 16 CPU computer. We call those cores, right? So you might actually look in the specs of your laptop and see that it's running 4 cores. Instead of making them go faster, we can now make them smaller and put more in the same space, okay? Computers are getting exponentially more powerful, whether that's because of speed or that's because I just have more computers in a chip. And that's actually one of the reasons that computers have such global impact. Because things that I could have imagined 10 years ago, okay, I couldn't actually do. I didn't have the computer power to do. I could have just dreamed about, right? And today, that can actually be happening in my phone, right, because of Moore's law. So it's like, yeah, it'd be so cool to be able to take a picture and kind of analyze it and find the text in it. I did that in my lab, and I had access to a supercomputer, and it ran for 2 weeks, and it finally found the digits. And now your phone can do it. Click. Oh, and by the way, it can translate from German.